Hello class, and thank you for watching. In lesson 1.9, rational functions and vertical isotopes, you're going to determine the vertical isotope of the graph of a rational function, and also you'll learn how to distinguish and determine again the behavior of our rational function around that said vertical isotope. Now, from the previous lesson, we discussed again the domain of these rational functions and identified what the values of x again are excluded from the domain by seeing where the denominator is equal to 0. Now today we're going to define again exactly what's happening at those locations that x cannot equal to 0. Well, at those values where the denominator doesn't equal to 0. What happened at those x's that makes the denominator equal to 0. So first of all, let r be a rational function where we have a numerator polynomial divided by a denominator polynomial, and these two, the numerator and the denominator, have no common factors. So there's not an x plus 2 on top, and for say an x plus 2 on the bottom with an x minus 2. All right, so that they do not have anything in common. So all these factors are going to be different. Now we know from the previous lesson that r of x has a 0 when the numerator is equal to 0. That's when we're going to cross our x-axis. And r of x is undefined when our denominator is equal to 0. And the reason for that is that there is a vertical isotope at that location of x where our denominator is equal to 0. So take, for example, this function right here. This function right here, we can see that if I get the top parts, 2x plus 7, set that equal to 0, and solve this equation for x by subtracting 7 from both sides and then dividing both sides by 2, that this graph is crossing the x-axis at negative 7 over 2, which is a total of negative 3.5. Which is around exactly right here, as you see right there. Negative 3.5. That's where we're crossing the x-axis. Now if we look at the denominator, x plus 3, and see what makes that equal to 0, we see that the denominator equals to 0 at negative 3. And if you notice, that is exactly where this red line is. So in terms of the domain, we say that x cannot equal to negative 3 because at x equals negative 3, there's a vertical isotope. Okay? An isotope again is spelled like this, but I'm just going to abbreviate isotope ASY. So we have a vertical isotope at that location. So that's why x cannot equal to that value. So the first thing we're going to go over, okay, is how is the graph behaving at that location? Well, if we're given a graph, we can determine again how the graph is approaching a vertical isotope. Let me highlight it right here in red for this example 1 right here. By looking at the limit of our function, we'll call this f of x. I didn't name it anything. As x approaches 1. But we can approach 1 from two directions. We can approach from the left end, so we can approach this red line from the left end, and we can approach this red line from the right end. To determine again which direction we're going to approach this red line, we can use this notation with a negative sign on the top, meaning the left. And as x approaches 1 to this function on the right side, which is denoted with a plus sign, we can distinguish again what's going on in those two locations. Let me just move this over and let me write that in. So this is the left of the vertical isotope, and this is going to tell us how the graph is behaving on the right side of the vertical isotope. So starting out with the graph, we can see what's happening to this graph right here. Okay, this portion right here, this graph, let me do it in blue. This graph, let me highlight it instead. This portion of the graph that I've highlighted in blue, as we get closer to this red line. So on the left side, as I get closer to this red line, I'm going to see the behavior of this graph. Well, this graph is pointing upwards. Okay, I'm looking at what's this direction of the graph. Well, this graph is pointing upwards, which is towards positive infinity. So from the left side, the limit as x approaches -1 of this function equals to positive infinity. And if I look on the right side, well, the right side of the graph, as we get close to the red line, is pointing downwards. So the technique, so negative infinity. So the technique is the same again as finding again the end behaviors, but instead of looking on the far left and far right, I'm looking at again as we approach the vertical isotope from the left side and the right side. And to indicate the directions, we simply use a negative sign to indicate the left and a plus sign to indicate the right of that value. And I forgot a symbol right here. This is not +1. That's my bad. This is x approaches -1. That's the vertical isotope. X approaches -1. That's the vertical isotope. Sorry for the confusion. Okay, so there you have it. So let's do some examples where we're not given graphs. Let's see what the behavior is, how the function's behaving as we approach again that vertical isotope. So for each function below, let's determine the equation of the vertical isotope and then write a left and right hand statement as x approaches said vertical isotope. So to find the vertical isotope, first of all, I need to verify that the top and the bottom have no common factors. And we don't. X minus 2 and x plus 3 is not the same thing as x minus 5. So to find the vertical isotope, I'm going to do the same thing as before and find the domain, figure out what's going to make this equal to 0. So what makes x minus 5 equal to 0? Well, x would have to equal to +5. So that is your vertical isotope. So we're going to look at what happens as x approaches that -5 from the left side. And what's happening as we approach 5 from the right side. Okay. And again, because it's a vertical isotope, it's going to behave the same. It's either going to point upwards, or as we draw, again, I'm going to draw a value. Here's my vertical isotope at 5. It's going to point upwards, or it's going to point downwards from one of the two ends. Okay. Maybe both ends point up, maybe both ends point down. One points up, the other one points down, and vice versa. Now to figure this out, well, all we do again is just simply, instead of using a number chart, all we do, since we're approaching one specific number, is pick a number that's going to be smaller than 5, but close to it. Not like -3 or like 0. We want to get as close as possible again to that line, like we did over here. Let me go back to the graph over here. I want to get as close as possible that I can to get that. So there's no way of me accidentally getting too far where it looks like the graph is going to be positive when it really should be negative. So I'm going to pick a number very, very close to 5 from the left side. So just to draw a number line, I'm looking at -5, and I'm going to get, +5. And I want to see how the graph is going to behave when I approach +5. So I'm going to pick a number very, very close. Not +4, not +4.5, but +4.9. Okay, +4.9. That's going to be very, very close. That's going to be like right there. So I'm going to test x equals to 4.9. So let's see what I end up with. So I'm going to do the same thing. I'm going to plug those numbers, that number in right here. I'm going to test that value there. So if I plug in 4.9 with 2, that's going to be positive. If I plug in 4.9 plus 3, that's also positive. And 4.9 minus 5, that's barely negative, but yet still negative. So this entire thing is going to be negative. So I'm negative again on the left side of this vertical isotope at 5. And I'm going to do the same thing on the right side. So on the left side, since it's negative, that means that this graph is pointing downward, so it's going to go towards negative infinity. Now I'm going to pick a point that is really, really close to 5, but this time from the right side. So I'm going to pick the number 5.01, or just simply 5.1. Just 5.1. That should be close enough. So if I put 5.1 minus 2, that's positive. 5.1 plus 3 is going to be positive. And 5.1 minus 5, that's still positive. It's just slightly over positive, but that's going to be positive. And the entire thing is positive. So the right hand behavior around that vertical asymptote is going to be positive infinity. So there you have it. So this is the behavior that the graph is going to have. Of course, we can graph this, and I'll show you again on tomorrow on how we can use the calculator again to graph this to see what the end behaviors look like. But we do need to develop the skill again for the non-calculator portion of our AP test. So this is your answer. This is the end behaviors using limit notation to describe the left and right limit as x approaches this vertical asymptote. Let's see, let's test another one. All right, so on this next example, number 2b, on example 2b, let's first find the vertical asymptotes. So our vertical asymptotes, first of all, we have to check that there's no common factor. So for example, look, this one right here and this one right here are common factors, so those do not count. So I don't have to worry about what's going to make x minus 4 equal to 0. I only have to worry about x minus 7 equal to 0. So x minus 7 equals to 0 means that x is equal to positive 7. That's going to be my vertical asymptote at x equals 7. And the reason I don't worry about this one is because that one matches to the top. The only places I have vertical asymptote is if there is no common factors. In terms of the domain, just to talk about what the domain is, well, the domain would be that x cannot equal to positive 4, nor can it equal to positive 7. But the only place where we have a vertical asymptote is at x equals 7. We'll talk about what's happening here at 4 tomorrow. So this is still the domain, but this is what we're looking for today. So let's look at what's happening on the left side as x approaches 7 from the left of h. And let's see what's happening to h as x approaching 7 from the right side. Well, all we're going to do again, imagine that we have a number line. I don't know why I make these two so big. 7. And we're going to pick something really close to 7, like 6.9 on the left side. So if I plug in 6.9 in all these places right here, we're going to get positive on the top, positive on the top, positive on the bottom, and negative on the last one. 6.9 minus 7 is going to end up being negative, so the entire thing is negative. So this is approaching negative infinity from the left. Now we're going to test the value on the right side, and I'm going to test 7.1. So if I test 7.1, that's a total of positive on 7.1 plus 1. 7.1 minus 4 is negative. 7.1 minus 4 yet again is negative, and 7.1 minus 7 is positive. So these two negatives again cancel, reduce each other out to make a positive, so no more negatives, so this entire thing is positive. So positive infinity. Let's move on to the next example. So right here again, our domain cannot equal to the bottom values, to these, whatever makes the bottom equal to 0. So it cannot equal to positive 2, nor can it equal to positive 3. But we don't have vertical asymptotes at both locations. The only place where we have a vertical asymptote is going to be at this factor right here at 3. because x minus 2 and x minus 2 is a common factor. So even though x can equal to those two numbers, the only vertical isotope that we have is at x equals positive 3. So now let's figure out how is the graph behaving as we get close to positive 3 from the left side up here on top and the right side right here in the bottom. So I'm just going to simply test a number that's going to be less than 3. So let's test x is equal to 2.9. So plugging in a 2.9 into these x's, we have 4 factors. So on the top, that's going to be positive, positive, and 2.9 minus 3, that is negative. So this entire thing is negative, so negative infinity. And now let's test a number slightly bigger than positive 3, so 3.1. We have 2 factors on the top, 2 factors on the bottom, and 3.1 minus 2 is positive, 3.1 plus 4 is positive, 3.1 minus 2 is positive, and 3.1 minus 1 is also positive, so everything is positive. So this thing is pointing towards positive infinity. And that's your end behaviors. Let's move on to the next example. This example, the top part is not factored, so we're going to factor the top part out. Our numerator, our denominator is good. X minus 2 is already a linear factor, so nothing to factor there. The top is not a linear factor. As you see, we have an x to the second power. So we're going to split that up to x and x. Now let's look at the signs. We have a positive sign. Positive and negative is negative. And we're getting the factors of 3. Well, 3 is a prime number, so the only works is 3 and 1. Now the reason that we did this is that we have to again verify that these factors do not match up with the bottom part, okay? So our domain here is that x cannot equal to negative 2, because that would make the denominator equal to 0. And the reason that it cannot make the that we cannot have x equal to negative 2 is because there is a vertical isotope at that location. So our vertical isotope is at that discontinuity at x cannot equal to negative 2. Now let's see what's happening again to this function. So as the limit of x approaches to 2 from the left, and what's happening as x approaches 2 from the right. So all we do again is just test, and we're going to test the value that's going to be less than 2.1, so I'm sorry, 2, so 1.9 for example, and plug it into the factor form, this one right here. We're going to see that the first factor, there's 3 of them, 2 on top, 1 on the bottom, well, 3 places to test this number. We end up with a positive, we end up with a positive also, and a negative, so this entire thing is going to be negative. So we say that this is going to approach negative infinity. And now let's test a different value. Let's have x equal to slightly bigger than 2, so 2.1. So that'll be positive, positive, and positive in the bottom, so all of this is positive. So positive infinity. And there is your vertical isotope right there. And here's the left end behavior, and here is your right end behavior. I know the first 4 again seem like they have the exact same behavior. all of them, the left is going towards negative infinity and the right side is going to positive infinity, but trust me, it's not always going to be the case like that, okay? Let's look at some more examples, some things again that are not factored. So here again, our factoring skills are going to be very essential to solving and finding the vertical isotopes and the behavior of this thing. So let's factor the numerator and our denominator. So we have x squared plus, x plus and x minus. So we have x plus and x minus. On the top we have x plus and x plus. Now 7's a prime number, so 7 and 1 are the only ones that work. And as you can see, a positive 7 plus a negative 1 is giving me that 6. And the factors of our denominator, the only ones that work with 17, since they're both positive, are going to be 7 and 2. So let's practice again the previous assignment vocabulary. So our domain will be all the values of x except for what makes the bottom equal to 0. So we cannot have the bottom part equal to 0, so x cannot equal to a negative 7 and x cannot equal to a negative 2. Now, why can't x not equal to these numbers? Well, because they're discontinuous. However, since we have an x plus 7 on top and an x plus 7 on the bottom, this is not a vertical isotope. We don't have a vertical isotope at that location. The only vertical isotope is the factor, is the result of solving the equation equal to 0 for the factor that is not in common with the top. So our vertical isotope is only located at x equals negative 2. And I didn't put the signs here, so we're going to look at negative 2 from the left, and we're going to look at negative 2 from the right. So let's imagine again we have a vertical, we have negative infinity, positive infinity. Just to help us out here, remember we have 0, negative 1, negative 2, and negative 3. So I want to pick a point that's extremely close to negative 2 on the left side. Well, that would be negative 2.1. That's on the left side of negative 2. And what number is going to be on the right side of negative 2? Well, the number on the right side of negative 2 would be negative 1.9. So let's first test x equals to negative 2.1 on the left side. So if I plug in those numbers into my factors, into this factor right there, this number plus 7, well, 7 is bigger, is going to result in a positive sign. This number minus 1, that's going to make it negative. Now plus 7, that's the same as the top. And this number plus 2 will be negative as well. So these two negatives become positive, no more negative sign, and we end up with a positive value. So plus, meaning that this left side, on the left side of 2, the graph is pointing upwards towards positive infinity. Now let's check the right side. Did I say left side over here? Because I did mean left side. Left side right here. Okay, so from the left we're pointing upwards toward positive infinity. Now let's check what's happening as x approaches negative 2 from the right side. So from the right, we're going to pick negative 1.9. Since this is negative numbers, negative 1.9 would be on the right side of negative 2 on the number line. So negative 1.9. So if I plug in that number into my factors, this would be positive, this would be negative, this right here would be positive, and negative 1.9 plus 2, that would be positive as well. So positive, negative, positive, and positive. Well, this simplifies to a negative value. So that means on the right side of negative 2, the graph is pointing downwards. So this is the limit behavior of our function from both sides of the vertical asymptote, and here's the equation of the vertical asymptote. And let's see, one more of that, so we can practice our factoring. So again, to factor this, we split up the x squared. The middle sign has first factor has to be negative, and since the negative times the negative is positive, the second factor has to be positive. So we're looking for the factors of 18 to give us 9. Well, that would be 9 and 2. I'm sorry, that gives us 7. Looking for the factors of 18, that give us negative 7. So with the signs, that would have to be a negative 9 with a positive 2. That adds up to negative 7. Now for the factors of the denominator, the signs would be the same. And the factors of 27 to give me 12. Oh no, they would have to be different. They would have to be, yeah, the same, and I still put different ones. X negative as well. Since a negative times a positive is negative, that would be negative as well. And remember, this sign matches up with that one. So now the factors of 27 that give me 9, well, that would be 9 and 3. And negative 9 plus a negative 3 equals negative 12. So our domain, I know it's not asking us to find the domain, but I like practicing previous skills, is that x cannot equal to positive 9, nor can x equal to positive 3. But we do not have vertical asymptotes at both of those locations. Since x minus 9 is a common factor, that means x equals 9 is not a vertical asymptote. The only vertical asymptote we have is at x equals 3. So that's the coordinate of our vertical asymptote. Now let's describe the behavior as x approaches positive 3 from the left, and as x approaches 3 from the right. So what direction is the graph pointing towards? So let's see. Well, let's test. It's positive 3. Well, that's simple. Again, we have 0, we have 1, we have 2, 3, and 4. So from the left, we'll use 2.9, and on the right, we'll use 3.1. So as x, let's have x equal to 2.9. That'll be negative, positive, negative, and 2.9 minus 3 is negative. So negative infinity. And now for the bottom, we'll test x equals to 3.1. So that'll be negative on top. On the first factor, 3.1 plus 2 is a positive value. 3.1 minus 9, that's negative. And 3.1 minus 3, that's positive. So these become positive, no more negative, so positive infinity. So there are your limit behaviors. Now, one of the things that we need to be able to use this idea and understand again the behavior around these vertical asymptotes is to correlate in order to match again distinct graphs and to come up with equations from the graph. So for example, let's look at the next page and let's use the fact that we know how to identify a vertical asymptote, identify zeros, to come up with an equation of a rational function that represents such graphs. So for example, let's look at letter A right here. We want to write an equation of this rational function. Well, we know two things. We know that if there is no common factor, a rational function is made out of a numerator function divided by a denominator polynomial function. And the numerator function, when that equals to 0, that's going to be our 0. That's when we cross the x-axis. Those are our x-intercepts. And if I see here, I see that I cross my x-intercept at 2. So I know that x equals 2. And since x equals 2, that means that my factor, this is my 0, is that my factor is going to be x minus 2. So I know my top is going to be x minus 2. And as long as there's no common factor, the way I'm going to determine the vertical isotope, again from what we're talking about today, my vertical isotope exists where my denominator is equal to 0. So if I look for my vertical isotope, I'm going to do it in red, I see that the graph splits up right here at x equals 3. X equals 3 is the vertical isotope. Which means that my denominator factor would be the opposite of this, and in my denominator I have x minus 3. So just again, reverse engineering this from the graph itself, I can come up with the equation that's going to cross the x-axis at positive 2, and it's going to have a vertical isotope at positive 3 right here. So this right here would be the equation that represents this graph. So there's your rational function. Let's see, let's try another one here, okay? Well, this one right here does not have a x-intercept. Notice that the graph does not cross the x-axis. Okay, the top parts doesn't cross again the bottom parts. So we do not cross the x-axis. So there's not going to be an x on the top. So our rational function, we'll call it capital R this time, a numerator function and our denominator function, the top part's not going to have any x. So we're just going to simply call it, we'll call it 1, positive 1. Okay. And now to figure out our denominator, we're going to look for that vertical isotope. That one, these rational functions always have a vertical isotope. And this vertical isotope, again, as you clearly see, is located right here at x equals negative 1. So if x equals negative 1 is my vertical isotope, that means that my bottom would have to be the opposite of x equals negative 1, which is x plus 1. So the equation to the rational function would be this. So all we're doing is just simply reverse engineering this. So the graph can have, again, this vertical isotope and with no, again, x-intercepts. So there can be an x on the top. I can't write this as x because that would mean that x would equal to 0 and I would cross the x-axis at 0. And since I don't cross the x-axis at all, the top part would have to be some integer, some number without an x. And I'm just simply going to pick 1. It could possibly be 2. Okay, but again, we're not going to get into full details what possibly is. So we're going to make it simple and just say it's 1. But there's nothing wrong with saying that's going to be 10 or 11 right now. But when we look at more values, we can clearly see that it's going to end up just simply being 1. Just stick with 1 for right now. Okay, now let's use the same strategy, but this time without the graph. Just again, the information. So the function has zeros at x equals 4 and x equals negative 2. Remember, our zeros, our x-intercepts, occur when n of x, the numerator, is equal to 0. So according to this, n of x is equal to 0 when x equals 4 and x equals negative 2. So that means that my factors are x minus 4 and x plus 2, the opposites of these numbers. So that's what our numerator function is going to look like. We're going to multiply x minus 4 and x plus 2. Now we have a vertical isotope at x equals negative 5. So we have a vertical isotope at x equals negative 5. That means that the denominator of this function has to be the opposite of minus 5. So x plus 5. And since it clearly says that we have a vertical isotope at that location, that means that this is not going to have a common factor with the top. So notice again, nothing matches top and bottom. So this is going to be our equation here. So for our next example, the function g of x has a 0 at x equals 1. So that means at x minus 1. And we have a vertical isotope at x equals 2, which is x minus 2. And x equals negative 2, which is x plus 2. The vertical asymptotes occur when the denominator is equal to 0 and the 0 the x-intercepts occur when the numerator is equal to 0. So our equation for r of x would be x minus 1 on top and x minus 2 times x plus 2 on the bottom. So our function would have to look like that. And now using limit notations. So here, limit notations indicating that as x approaches negative infinity, the left end is going to negative infinity, and as x approaches 1 from the left side is equals negative infinity, and as we approach 1 from the positive side, our function is approaching again another negative infinity. These statements again simply means that this is your vertical isotope. If we're approaching a value, numerical value 1 or any constant from the left or from the right, and it's equaling to an infinity, that means that we have a vertical isotope at that value that x is approaching. So since x is approaching 1, that means that x equals 1 is a vertical isotope. And we can only get a vertical isotope if this x minus 1, the opposite of this number, is going to be, again, what makes the denominator equal to 0. So x minus 1 would be a factor of our denominator. So r of x will have to equal to some number, because we don't know if there's any zeros here, because we're not given that fact, but we are given that we have a vertical isotope at x equals 1. So that would mean that our denominator would have to be x minus 1. Again, just reverse engineering this. So this would be the function that represents and correlates to this concept that we have a vertical isotope at x equals positive 1. All right. So that concludes our notes for lesson. I'm going to scoot back up. For lesson 1.9, rational functions and vertical isotopes. The next lesson will discuss what happens at these locations where we have a common factor. Okay, why can x not equal to 4? Like on this one right here, why does x not equal to 4? All right, and what's happening when we have a common factor on top and the bottom? Because we don't have vertical isotopes at the location, we are going to have something else at those locations. Right now, the only places we have a vertical isotope on this one was at 7. All right, like I said, that concludes again our notes. Like always, I appreciate you watching, and I hope you have a great day. Goodbye.